So the final application of that fundamental theorem of calculus is going to be really helpful when you have an initial condition, which is how you can solve for your plus c and things. So let's do it generically first and then show you a couple examples. So when you have a function dy dx defined as, you're given the instruction and you have the initial condition of a c, that's your plus c. So a is the x value and c is the y value. Then when you apply the integral on both sides, so we're going to separate dy equals f of x times dx, so that's the separate part that we learned early in the chapter, separating the y terms from the x terms. And then you integrate, separate, integrate. So we're going to do integrate dy, integrate f of x dx. So the integral of y, or dy, is y. The bounds go here. All right? We are going to set it up as a becomes your lower bound. That was the part of the initial condition, to an unspecified upper bound. And the plus c is added at the end. So this is how to set it up generically when you are given an initial condition. Oftentimes this is applicable when the function is not something you can integrate very easily. It doesn't have a nice antiderivative. So you might set it up and then just show that you know how to set it up, and you won't finish it unless you've got a graphing calculator you're allowed. So let me show you how to do that that was sort of a generic way. Let me show you a couple quick examples. So you'll be asked to solve dy dx equals e to the x tan x, and you do not know how to solve that yet. And the initial condition is going to be 8, 0. So we separate dy equals e to the x times tan x dx. We integrate both sides. So y will be the integral of e to the x tan x dx from 8, which is the value of the initial condition, to an unspecified x, plus 0 as the constant value. And you're just going to set it up and leave it like that for now, because you don't know how to do the antiderivative e to the x tan x dx, and we don't necessarily have an upper bound, so we can't use a calculator to solve that. I'll show you how to do that with a calculator on a different day. All right, another one to set up. So that is considered solved because y is by itself, and you've used your initial condition. So another one might be to solve dy dx equals the square root of the quantity 3 minus cos x, and the initial condition on that is negative 3, positive 4. So we're going to separate and then apply the integral. So separate, integrate. So y by itself will be the integral of, my lower bound will be negative 3, my upper bound is x. 3 minus cos, I realized in the second problem I forgot to change. You're not supposed to use the same variable in your bound as you do in the lower part, in the function part. So change to a variable. It doesn't matter. You could use a's or q's or w's. T is the most common. I forgot to do that in example 1. I'll go back and do that in a minute. But if you're going to use x as your upper bound, which is what they want you to do, change the variable to something else in the expression of the function, and then plus the initial condition of 4. And that's it. Okay, that's considered solved because that integral, 3 minus cosine x under a square root, is not something we can do the antiderivative of. So I'm going to correct this a minute and make these t's again. Tangent t dt. Okay, so The only way that you could continue with a problem like that is if you had a second point. Okay, the only way you could solve that is if you had not just an initial condition, but a second value as well. So suppose that you were wanting to solve that, the same above question, so continued. Solve for x when, say, y is 7. And so then you would set up, and you could, if you had an additional point, set that up and solve it, t dt plus 4. And so you subtract 4 from both sides, so that'll give you 3 equals negative 3 to x of 3 minus cosine t dt. So I just subtracted 4 to both sides. And then you'll use your graphing calculator, and you'll set this up in y2, and all of this would be set up in y1 using a math 9. And then you look for the intersection of those two things, and that would give you the solution for x when you did it if you had the graphing calculator. So the only way to go farther with one of those questions is if you have more than just an initial condition. If you have an initial condition plus another value, then you could continue solving, but you'd have to have your graphing calculator to do that and to look for the intersection point. And so it took my calculator a little bit of time to graph that, because it's working hard to graph an integral, but we came up with negative 1.638 as the solution for x. All right, good luck with this last assignment of Chapter 6.